We will talk about DNA codons if we can get where we want to be at the end of class. If not, we'll do it at the beginning of next one. If I look at letters here, and I'm finding in this table UUU, I also have a UUC, so uracil. They both indicate that they're after a phenylalanine. So with a 3-letter code, which is the codon piece that we code for RNA into actually getting amino acids, there's multiple variations that exist. But their frequency of these, if I were looking at frequency, is not always the same. So just because I have these both, is their frequency they're found the same? The answer is no. They do change. Some are much more common than others, and the question might be why. And turns out that some are favored. This has to do with not only the wobble position and its favorability, but also there's a biological use, and different systems actually have different prevalences in their biological use. They're not always the same in all organisms, by the way, that frequency chart. It varies. So it's kind of an interesting thing to look at. When we do talk about the wobble position, we are always looking at that last of the nucleotides, nucleobases that we're looking at in that pair. Okay? And so what you are looking at here, this is leucine, right? 3 prime, 5, when we read 5 prime to 3 prime, as it's put in here, when it matches the mRNA pair, there is a substitution wobble pairing, and that is in this position always the one that is sort of forgiving, and it has options that exist. Okay? And
so,
yeah, go ahead.
Does this just mean that you have one codon that's your primary one that your system would want to use, but you have some wiggle room for in case a mistake is made?
In case a mistake is made is a good way to look at it. It's also can argue for frequency of how well that would be transcribed as the information, how hard it is to get that into actual protein codes.
Okay.
So some are going to be preferable. So yeah, we see some of that. There's this silent mutation in this. If I were looking at this June of 2022, this may not, these synonymous genes are most strongly non-neutral. There's actually a fitness exam that we can have. So if you get a mutation like that, it's actually less likely that that species, if we're looking at single-celled organisms like yeast here, that they'll survive or thrive. Meaning, genetically, we're actually aware that it can work, but it's likely that the protein amounts won't be the right ratios, which can lead to inadequacies in somebody thriving, if you're talking about single-cell organisms. And we believe that that translates also into higher organisms as well. So, yeah, fascinating, right? We're just learning about this. We've known that there was differences in frequency, but this is still new, and so we're in the discovery phase. Okay, so yeah, things to sort of learn and discover. Here's some of those minor nucleosides that exist. Inositine, put in there, made by deaminating the adenosine. What do I mean by deaminating?
Taking out an amide group.
Yeah, that's all we're talking about. A pseudo uridine, okay, found widely in these, common in eukaryotes and also in new bacteria. May help in the folding of it. So these are some different pairing positions that can exist with that, and we're still hydrogen bonding. And what is the frequency there? So there's some deamination events, abnormal linkages that we can have for where the ribose sits, or sulfur put in the wrong position, so. Just a side note, is everything that we look at, if we're looking at other minor nucleosides, are they always used strictly for coding of genetic material? And the answer is no. Here's some very common ones that you should be familiar with, but you may not realize it. This is called the xanthine class, and this is the one that you famously know. It's called caffeine. This is actually data extracted from cocoa. One of the first jobs I had in the industry, I would actually get cocoa powder. It would show up in the lab. I'd open up my sample, and that smell of cocoa there. And you'd want to do the same thing that you would do when you were a kid when you smelled cocoa, right? Put your finger in it, but you knew not to do that in the lab, right? But what does that taste like when you taste that cocoa powder?
Bitter.
Bitter. Why is it bitter? It's basic.
Always because it has a lot of amines in it?
Yeah, it's called a nucleobase for a reason, right? Most of us do not recommend going and trying a detergent or some sodium hydroxide so you can taste that bitter taste for a base. That one's okay. You can taste that one. Okay. Caffeine, by the way, is also known as a flavor enhancer. It actually changes the palate of your tongue because the bitter taste actually helps complement certain things. Coincidentally, when you're looking at cocoa, is it always the same where I get it from? What was the country of origin of cocoa? Yeah, it's down in Brazil, down in South America. That's really where we're looking at. Potatoes, where did they come from? The Americas as well. What about vanilla? The Americas. What about corn? The Americas. Yeah, most of our modern diet, it's all American food. We're like, hey, it's all about tomatoes. Where were tomatoes?
America.
You guys, you gotta learn some history, right? So, yeah, I mean, it's really problematic. It's like, so about the European chocolate. It's like, well, we had it first.
We.
They did. Theobromine is actually very high concentration inside your cocoa powder. Theobromine does what? It also lowers your blood pressure.
Wow.
Decreases risk of cardiovascular disease, may reduce some of your bad cholesterol and improve your good cholesterol. Fantastic. And it's not about the roasting of it, but it turns out the region and where it's grown and the weather that's going on, the humidity, the temperatures, how cold it gets actually affect the seed, which is where these are extracted from. So
Cool.
By the way, not that we care, but that's true also of coffee, which also is from the Americas, right? Okay, great, yeah, we're all Americans. All good. Okay, so these two names, it would be a crime if you didn't know them. Watson and Crick, they're, okay, this is about DNA, right? Their statement, this structure has novel features which are of considerable biological interest, okay? Science in action, value of collaboration, cost of sharing your data too early. Yeah, so in 1929, Levine and London look at the structure of DNA. By 1935, Levine and Tipson are getting closer in that structure, and we're starting to understand it. Chagraf in the 1940s comes up with this base pairing rule, which works beautifully, and it's one that we're going to actually work, and you'd want to get this right on the test. If I gave it to you on the test. If I did that, that would be obvious, right? But A goes to T, and G goes to C. So if I actually knew, interestingly enough, if I knew just one, could I figure out the other three concentrations?
Yes.
That's really weird, but it's kind of cool. So let's try it. Okay, go for it. Give you a minute.
Oh, wait, so X and Y.
Right, because you get my 64 divided by 2.
Yeah. Because you know that T only has the admin. These two. That's, you also need equal amounts of T. And then you do 100 minus that number divided by 2 to get C and G.
Yeah, you can get your own CG. But what's the second thing about that?
Can you wear that in?
The 17 is 4.
I found it in the test. And
So for 17.
Once you've got it, check, make sure that your table's getting this.
Okay.
Now let's double check those results, but it should be coming in, you should be able to
They
do
would
this.
see me doing this. It's like 32. 6, 7. It's a no test. Okay. Why not?
Jimmy's like 10 of those on the exam.
Yes.
Biology's on this.
This
is a life pathway.
They got this, but about bring it on.
Give us like 5 questions of that.
I know.
Can you give us like 10?
Can you have a bonus question?
I might give you one of these, that'd be alright.
Okay. Like an extra credit.
Species X. A equals T, then 32% would be also 32% of T, which is 64% of the total composition, leaving me, if both the AT plus the GC equals 100%, then the other one must be 36 for the GC, which means 18 and 18, right? Then likewise here in species Y, we could figure that out, right? Okay. Everybody good with this? Okay, don't get that wrong. That's supposed to be a gimme, right? So, all right, good. All right. The double helix. So Watson and Crick and Wilkins share the Nobel Prize. Franklin, who really had the data of the X-ray crystallography data that actually brought to bear the cross, the diamonds, cross meaning helix, diamonds meaning the phosphate sugar backbones on the outside. And she was able to calculate the parameters, of which Watson and Crick then happily fit the data. Was it really that she was not, that she was a woman, that she wasn't given credit? It doesn't have anything to do with that. Why wasn't she given credit? It's right there. She died. We don't give Nobels posthumous. That's not done. So as a result, and has that happened to others, by the way?
Yeah.
Yeah, that has happened to others, male and female. I mean, so it's sad, but that's the way they work. So, by the way, if we were really honest with the data and you read the history on it, Wilkins and Franklin, they did not get along well. She was really she's a strong woman. Dominant personality in the lab is what history and journals would suggest. Wilkins actually might have solved the whole puzzle himself had he not had emotional problems with having a woman in the lab. He wasn't man enough for that. That's my perspective on it, okay? Just get over it, just do work. Yeah. So it matters very little what my opinions are on the history, but it's an interesting read. And Watson and Crick sure took advantage of that situation. There you're looking at her data. See the X? Yeah, and then you're seeing the diamond patterns. These were the diamond patterns which we were looking for, okay? All right, so X-ray crystallography means that we need the crystals of the structure to do that. There's these guys, you can read a little bit of the background on it. Yeah.
I was alive.
Does that so James Watson's still around? Is that what that means?
Yeah, it was very recent he died. Yeah.
Okay.
Dang! Yeah, I thought these guys were long gone.
It's all relatively
So,
recent.
in this illustration, the major and minor groove are being pointed out, sometimes in looking at those, you're not sure what we're really illustrating. It looks a little easier here to see the minor groove versus the major groove because you can see the spacing in the major groove is much bigger than the spacing in the minor groove. I have brought a model here created by Brother Lemon. Beautiful little model. This is the minor groove. The major groove is the big one. The major groove is in almost all cases where we actually get binding of the proteins that actually interact with it to do transcription factors, to actually help open and close the DNA up. Yeah. It is because there's more space where it can interact with those nucleobases. And so that's really what we're talking about. But the question might, do you see something here? 3.4 angstroms in order between the spacing here. 36 angstroms to do what? A complete revolution. So, okay. So if we're talking about this, does this sound familiar when we did this with amino acids doing alpha helix? People do this math too, it shows up, okay? I'm not gonna do that to you on the test, at least I don't think I am. But you should know that in the back of your minds because that trivial information can certainly come out in various tests that you would see in life, so that's good to know.
What's the
Yeah.
question?
So as far as the major and minor grooves, what causes them to be major and minor?
Yeah, that's exactly where we're headed.
Okay.
Lee?
Oh, same question.
Good, perfect, you guys read my mind. So 240 degrees up here, 120 here. What are we talking about? It means if I pull this out here, and I'm looking at this triple bond, now this seems really trivial because it's not quite the same. Is there an acute angle and an obtuse angle in this? The actual answer is yes. So as it's going around in a circle, as its base pairing, and it's forced to do so with the ribose as they link in the phosphodiester backbone, one side of it is acute and one side is obtuse, meaning the longer, the angle's greater than 180, the other one's less than 180. That happens in all of these. As you do these, you're going up, and so it turns out that the side that's acute follows the same one. That makes up the minor groove. The one that's obtuse makes up the major groove. So let's watch a little bit on that. This is really what they're talking about as we do the base pairing. This one, I just told you one piece of it is the acute and major. I'm going to show you the other piece which drives the reason it does it cyclically instead of just straight columns, and that's driven as well by the sugars and the way that they point in going 5' to 3'. Yes, great.
Anyone can use to improve their hearing almost
Oh, sure.
overnight. Did you know that
I see, okay.
In this animation, the major and minor grooves of DNA are highlighted. Nucleobase atoms facing the major groove are colored pink, and nucleobase atoms facing the minor groove are colored blue. It's easy
These
to
are,
see
this
that
is the
major
second
groove is
part
larger
of
than
what
the
I'm
minor groove.
explaining for the
For this
reason why.
lesson, we will look more closely at the structure to get a more precise definition of the major and minor grooves. If we focus in on the deoxyribose of the backbone, we can see the important relationship that defines the major and minor grooves. Looking at the left backbone, we can see that in the major groove, the deoxyribose always points its ring oxygen up. If you imagine the deoxyribose as the Statue of Liberty with the phosphate as its torch, you'll always remember the correct orientation for the left side of a major groove. Looking again at the left backbone, we can see that in the minor groove, the deoxyribose always points its ring oxygen down, kind of like an upside down Statue of Liberty. This orientation makes sense because the two DNA backbones run in opposite directions. Always keep in mind the 5' to 3' directionality when viewing polynucleotides. Looking at the right backbone, we can now see that in the major groove, the deoxyribose always points its ring oxygen down. This is the opposite orientation compared with the complementary left backbone. And looking again in the right backbone, we can now see that in the minor groove, the deoxyribose always points its ring oxygen up. Again, this is the opposite orientation compared with the complementary left backbone.
Okay, so what's holding these together?
Hydrogen bond.
Well, hydrogen bonding between the
Hydrogen
two.
bonding between them. As they're hydrogen
DNA
bonding.
stands for deoxyribonucleic acid.
So
It is a
that's-
type of nucleic acid, which is one of the four major
I'm
types.
glad you're excited about that. Okay. All right. Oh, not one that one. Okay. So as we jump around here and we're trying to learn and understand that, one part is acute obtuse angle, and you'll see this in the textbook. This is really what we're highlighting here. This by far is the major reason, okay? But the other is the fact that as it's going up with your Statue of Liberty up and down and whatever, just looking at that phosphodiester backbone, as it's curling up and down and then it's hydrogen bonding, it causes it to actually twirl because of the way the angles work. And is the sugar locked into a specific position?
Yes.
Yeah, it is, as we look at those sugars. So that's really where it all comes to. Now, there's always a few questions that revolve around that. I've just given you the facts. Is anyone still asking questions? You're welcome to. If we're good, let's go forward because we got a lot of ground to cover. But go ahead, Lee.
I'm a little, I don't know. I don't know.
It's okay to ask the question. Some others are probably still asking it, not daring to ask it. So you understand if I have an acute angle and I go up, I'm gonna get a thin vein up,
Yeah,
right?
but like why is there a difference in the angles in the first place?
Well, so that's driven by the actual what?
Just the like size.
The way that the bonding works when a hydrogen bonding does it in a linear fashion, right? But yet because of the way that the angle's working here, what's it doing? This side
So
is.
it's
It has
always,
to rotate the like
It's
the sugars
acute
are
on
going-
this side and obtuse on this side, and then as it's rotating, that's really causing that.
so to make sure I understand this, right? So when we're talking about acute versus obtuse, we're talking about if you were to create a straight line between the nucleotide bases,
Yep,
okay, and then because the sugar is always below the nucleotide bases because of how it's attached to the
Yeah.
sugars, that's why we have an acute and an obtuse angle. Okay.
okay. Good. All right. Okay. Proteins binding inside of that. Here you're looking at glutamine or asparagine. Nice hydrogen bonding opportunities that can occur. Arginine also able to get in there and play part of this game. There are certain structural motifs that are well recognized to respond to that major groove. There are also a few that respond to the minor groove. Remind somebody else what a structural motif was, and then let's go forward.
Oh yeah, I have beta terminate,
For those shapes.
random coil, proline,
So
beta
like,
terminate.
what do you mean by structural motifs?
About a thousand
the-
different structural
bunch of
motifs
THCA, so
existing. Certain ones are well recognized to be interacting with DNA. Yeah, go ahead, Kevin.
Are proteins that bind to DNA, is that like a typical example of like mRNA? Or is it like, are there other more proteins that bind to DNA?
So
During like transcription and stuff?
All your transcription factors
Like
are obviously
mRNA and things that kind of come in and bind
Yeah,
to DNA, right?
yeah. Okay. There's a helix structural motif in the lacopron and the lactopressor of that. Just different ones that we're looking at. Zinc fingers. It is not important that you know all these, but we know the specific amino acids, which are reacting at which spots, which nucleobases. As you learn to recognize this, and we look in an age where CRISPR is becoming more and more common, the ability to say, what is the fidelity that it will find the right spot, which is what currently, as we look at using CRISPR in humans, and the FDA is approving methods where we could do that for different purposes like beta thalassemia and sickle cell anemia, is it going to be reproducible? If it causes a mutation that causes death to somebody, is that acceptable? And in their world, they're saying, we can't have an accident. We have to know it's right. So they'll be looking for those numbers. What's the frequency of that? On the right on, the other piece that will show up is the piece that we're already starting to lead into. Nucleotides, as they form DNA and RNA, actually have three-dimensional structure. So what does DNA's three-dimensional structure look like? Now, you know that ultimately, that it's a double helix, right? This is something called the A form. It exists only in the lab, okay? It's when we have it dehydrated, it doesn't have as much water, it exists in the lab. B form is the most common that we see across nature in us. This is the one that you're used to looking at. Z form is
like a
the
problem.
one that is
that
also
encoding?
found in us. What?
Is that during coding or transcription?
Okay, so it actually just exists in your DNA. It's found that way, and when we do that, do you remember that conversation that we had about whether or not I would do it sin or anti?
Yeah.
I said there were some of us that had, all of us that have a little sin in our DNA, it's just encoded. So Paul was totally right when he said all have sinned and become short of the glory of God. Yeah. Z form is exploiting that. Would this, now going back to your question, would this affect ease of transcription?
Looks like it.
Absolutely. Very exposed, easy to open up and deal with. So it's definitely going to change that. Okay.
So is the Z form just because of mutation that it exists that way, or?
Yeah.
Okay.
Yep. Typically found with sequences alternating in the purine, pyrimidine over long ones, anti-pyrimidine sins for the purines, and that's what's usually causes. This one's right-handed. Again, these were really the same one. All they did is take the waters out. This is the left-handed in the way it's actually composed of it, okay, as it spins. Kind of weird. Different angles, 3.4 helixes per rise, right? 10.5 per full turn to get up that 36 angstroms, right? So hopefully all of that's helpful for you. You see some green there. You would want to know all three of these forms as being standard DNA, but A is the one that's lab formed, okay? Do you need to know all the details? No, but if you're learning any of them, learn about B form. But what would you want to know about Z form? It's left-handed, and it's doing it with also some sin in there, okay? So, and it's more open, right? DNA could also be done in different ways that are weird that we do in the lab. We could get triple-stranded DNA. And that's been hypothesized for use in actually controlling cellular metabolism.
Really?
Essentially a transcription factor. We call it Hookstein pairing, sort of pairing the backside of it, triple bond. So I'd have to have a sequence that would match just right on the outside of it, and it's kind of a funny way to do it. So there you go. By the way, we also have successfully created tetraplex DNA. Fantastic. I see no purpose in this one, but it's interesting.
But wait, there's one more. Why is it?
Well, right, so what we're doing is we're characterizing what forms of DNA. Now, DNA is what? Short or long? Long, okay? DNA is long. And so as we think about them packing, right, then they get round around the histones and then they're stored away, but it's long. Now when I move over, again, 5' to 3', and then the other one running 3' to 5', okay? So we want to get to discussion of that anti-parallel in those chains. Watson and Crick, their brilliance, right? It has not escaped our notice that specific pairing we have postulated immediately suggests a possible coding mechanism for genetic material. And were they right?
Yes.
Yes, that's really the big deal, right? Nobody knew where the code was, and this is where we found it. It's like, oh, and then we just had to crack it, right? And once we had, all answers would be known, but it turns out that they aren't. When I was in my undergraduate, we were just starting sequencing it, and the cheer was, we're gonna know everything when this happens, we'll crack everything, and then we solved it, and it was like, okay. And then I went back to graduate school, and it's like, yeah, we don't understand anything still. Congratulations. Replication using polymerases, right? So this is a beautiful illustration of DNA in action. Now most of you should have already seen this. Notice these are proteins here. We're making a copy. This, if I could get it to do what I want. Oops, hang on. Let's get out of it. Good. We're going to jump into this really quick.
Using computer animation.
Don't want to watch a lot of this. We have other things to
We are now
do.
able to see how DNA is actually.
These are proteins.
You are looking
Conformational
at
changes.
amazing miniature biochemical machines that are pulling apart the DNA double helix and cranking out a copy of each strand.
All working in series.
The DNA to be copied enters the production line from bottom left. The whirling blue molecular machine is called helicase.
So helicase on the front here.
DNA as fast as a jet engine as it unwinds the double helix.
Proteins working as fast as the jet engine. Unwinding.
One strand is copied continuously and can be seen spooling off to the right. Things are not so simple for the other strand because it must be copied backwards. It is drawn out repeatedly in loops and copied one section at a time. The end result is 2 new DNA molecules.
Okay, so fairly impressive, the way that's put together. Hopefully in doing that, you feel like you're a little bit smarter, having looked at some of that with me. And also impressed at God's handiwork, that he can do that. 3.8 billion base pairs in our DNA. When you're looking at the part as they come apart, one strand, just copy it off the template strand, new writing 5' to 3'. Okay, beautiful. The other, I'm creating 5' to 3', but they're coming out in fragments. They're called Okazaki fragments, okay? And then those have to be stitched back together in order for that to work. And they were mentioning that in the clip. So much information, again, to cover. Just some basic anatomy of what's really going on. You could see that would be just awesome to go into every piece of detail of that, but we've got the idea. Proteins, structure determines function, conformational changes, things are happening. The one thing that I might mention here though, that sometimes is mind-boggling. If it's going that fast and it's creating a copy that fast, what's the concentration of the nucleotides must be inside of your.
It's really small though.
It's insanely high concentrations, right? In reality, in a very small space. It's also able to sort and put the right one. And it's dealing with those that are deoxy as well as those that are oxyform, RNA versus DNA, and it's handling it all. Yeah, go ahead.
There's a question on the study guide. I think it was like kind of in between kind of what we just covered, but when it comes to the level of conformational flexibility between DNA and RNA.
We're getting there.
Okay, I wasn't sure. I thought we
You're
just skipped it.
you're
I'm sorry.
absolutely right. So messenger RNA, ribose, right, contains uracil instead of the thymine. there's our single-stranded one, Kevin, exactly where you're headed. Single-stranded RNA, is RNA flexible in comparison to double-stranded DNA? And the answer, of course. But you already know that DNA can be wound around histones, so you're like, oh, it has obviously some flexibility. But is RNA usually found in its open form like that? Yay or nay?
Yay.
Answer is no, it doesn't like that. It likes to instead find a partner and pair with it. That's the way it's most stable. Is RNA, though, in making a copy, is it short or long? Generally speaking, when we're making that, it's short pieces. So as a result, we run into these issues. Something known as a palindrome. Now my daughter's got a name of Hannah. She loves that her name is a palindrome. And she knows that word even though she's only 8. She's known it since she was 6. My name's a palindrome. Okay, so you can get it, okay? It's just whether I go forward or backwards, it's the same in the way we read it. That makes beautiful sense, except for when we get here, which one's considered to be the palindrome is messy, because I would have thought that we were talking about it this way, what's called a mirror repeat. But the way we talk about it inside of biochemistry and genetics, the palindrome is found where? Where's the repeat on either way?
Oh.
Opposite strands. But it has a defect as a result of that. What is the pairing if I start pairing these?
They could pair up.
Because I have a palindrome sequence, its matching sequence is it can fold on itself.
Yeah.
Which creates by default, yeah, you don't need to know all that, but you should need to know what a mirror repeat is and a palindrome is, okay? But a hairpin loop, when we're talking about secondary structure, is a secondary structure. Just like we talked about alpha helices, beta strands, beta turns, beta sheets, right? Now we're talking about secondary structure. Here, this is a secondary structure formed from the primary sequence. Go ahead, Jacob.
That's a result of the palindrome?
That is a result of the palindrome. And you can see how that's working, right? Because of that existing palindrome sequence.
And they never have to be perfect palindromes.
They don't. They don't have to be perfect, but they should have this beautiful matching pair. Okay, so there's a hairpin. Hairpins are not the only secondary structure we're interested in you knowing the vocabulary for. There also exists something called a pseudonut. There also exists something called a hammerhead. This one looks like a little hammer, right? Cool. Yeah, look like knots, okay? So these are different names. There's also something known as a crucifix form.
Oh.
It's like two
It's like a double hairpin.
Hairpins, one on each side. Okay, that's kind of cool. All right, so when we use these, okay, RNA then starts creating structure, tertiary structures. Has it ever crossed your mind that your ribosome, which acts as an enzyme, must have a set tertiary structure? And it's coded for inside of your DNA. Has it ever crossed your mind that your tRNA, which is recognizing specific amino acids that it interacts with, and it's recognizing the specific codon sequence that then it interacts with as well with the messenger RNA, that too must have a set secondary tertiary structure for it to react and behave properly? If it hasn't crossed your mind, this is how it's done. Those secondary structures then go into that, and when we do that, they form things like the tRNA, or the hammerhead piece of the tRNA, right? You're like, oh, gotcha. Introns. Does it matter? Yeah, what do bacteria do with introns? They don't like them. Yeah, they can't handle it, but you can. Okay, well that's good. I'm glad that you can handle it, but they can't. Makes you different than them. Okay. So in the write-on question that Kevin's alluding to, you now need to be able to talk about what is the difference between RNA and DNA. One's more stable than the other, right?
Yeah.
And you know why, so that you don't flunk biochemistry, right? Including the mechanism, which will be on the write-on in the very same area that you're writing about what are the structural differences between DNA and RNA. as you describe them, you're gonna say, well, DNA could be, it comes in double-stranded, it's very long, it likes to base pair, double-stranded helix comes in A, B, and what's the other form? Z, great. And then it could have been triple or quadruple-stranded, fantastic. Well, whoop-de-doo. Now, does the DNA have palindrome sequences?
Yes.
Why doesn't it fold like that?
Because it base pairs.
Because its base pairing to its long length is preferable to short spans. Massive copy length is favorable to short strands. And so that's what's favoring. But the RNA, in its short strand without that long partner pair, it likes to favor these other ones. Okay. Does RNA also come in double strand? Could it come in an A form, B form, Z form? Absolutely. It could, okay? But it's short.
So just to confirm,
yeah.
even when it's double-stranded, it's going to be short?
So RNA is short. Does viral DNA, is it reasonably long? RNA, yes,
Yeah.
Yes, it can be. It can be longer. Anything that DNA does, RNA can do as well if I make it longer.
Okay.
Right, and anything with DNA, by the way, if I make it shorter, could also do the same things that RNA does, which has to do with how we would create something known as aptamer arrays, which are actually like DNA antibody pieces. Pieces that recognize and grab certain structural motifs, grab certain molecules with high fidelity, only they're not made out of protein. They're made out of DNA, nucleobases.
I just want to make sure I understand. So the hairpin is considered a secondary structure?
Yes, and so is the pseudonaut and the hammerhead, and you'll want to name those on your right arm.
I just want to make sure the other ones were also the secondary.
Yep, and the crucifix.
Okay.
Yep, so if you're seeing where I could get points from, crucifix, hairpin, hammerhead, right? You think, yeah, I can do this, right? A, B, Z, triple, quadruple. Yep, okay. If I'm looking to denature DNA, I could look at the UV absorbance. If base stacking is lost, UV absorbance increases, okay? So I start opening this up, what's gonna happen?
The absorbance.
I'm gonna see that. So, okay, lots of things. This is thermal denaturation. We're heating it up in order to open it up. We're looking at 260, that makes perfect sense. What do you see as the temperature increases? It's melting. TM is the melting temperature melting for that DNA. We had something very similar for our proteins. This is just pulling those apart, okay? High GC content actually increases that TM. Why would that be the case? Tell a neighbor that you know why that would be the case.
Because more volume.
Okay, so hopefully you just answered the question by saying, well, it's obvious I get triple pairing on the hydrogen bonding for my GC versus the AT. Okay, beautiful. Longer the DNA, the higher the temperature. Salt and pH affects things as well. There you're looking at the GC content. As that changes, obviously it affects the temperature melting. You can see it's highly correlated. Pretty good fit. Yeah, Connor.
Does that mean that we
Does
can
that
actually
mean that what?
identify the differences in DNA by its melting points?
We might be able to characterize that the DNA might have harder ability to transcribe that region if it's got what? High GC content. Where might organisms use high GC content might be in extremophiles. Oh, if I'm living inside of a high temperature thermal hot pot, maybe I need to have something so my DNA doesn't fall apart. Oh, that makes perfect sense. That's really what we're talking about. Versus if I'm working in really cold temperatures in the Arctic, my organisms probably don't want a lot of high GC content because I'm never going to get it apart.
Yeah.
And that actually correlates fairly well. okay? All right, lots of awesome stuff. Deamination, depurination, big deal. We're talking about mutations that occur all the time inside of, on a daily basis. Really, deamination, which is the removing of an amine off of your nucleotide, happens. How often? About 100 cysteines going to uracil every day in a single mammalian cell. Oh, depurination, losing the actual purine, having the glycosidic bond hydrolyzed, losing it, about 10,000 purines lost per day in a mammalian cell. Your body, God created with proteins that go along and repair that. So despite the fact that you've got 3.8 billion base pairs and these mutations are happening all the time, every day in each cell, you don't get cancers most of the time. By the way, you all probably have cancer, just so you know. You'll kill it on a regular basis because your cells will function just like they're supposed to and you'll kill it. But at some point you might fail. But this is one of the reasons that's occurring, okay? So that seems reasonable. There's what deamination means. Again, popping an amine off, that's gonna affect things. Yes, I can deaminate lots of things, okay? Okay. No enzyme required. Just happens. Do things actually promote it to happen more frequently, though, than what we normally would see inside of a cell every day? And the answer is yes. Things like sodium nitrite, sodium nitrate. Where are these found? Somebody say it, meat. Your salami, even your turkey that's deli meat stored. We use this as a preservative because it makes our meats last, and we like that. But what does it do to your body? Increases the high likelihood of causing cancer. Oh, okay. Nitrosamines there. That actually probably has something to do with this weight. The average hot dog weighs 1.6 ounces or 3.8, about 45 grams. Why? Because when I look at processed meats and the risk of cancer, what do we look at? Okay, here's the take home. Carcinogenity of red meat and processed meat. It turns out that I have a 17% increase of risk per 100 grams of red meat and 18% per 50 grams of processed meat. One hot dog
an 18% increase
per day will give you an 18% risk of your cancer. Now, we're talking about what type of cancers? Many, but pancreatic, prostate cancer, okay? Wow. Okay, colon cancer should be on that list. Those are exposed to the food that is in your gastrointestinal tract. You've got that food with high salts in there. Those salts are affecting it. That's what's actually promoting it. Oh, got it. Okay, so that is the story. By the way, do you guys know what the odds are that you'll get colon cancer? 1 in 20 will end up with colon cancer. So if we give you essentially an 18% increase, we've gone from, instead of a 5% chance you're going to get that in your lifetime, what have we gone to?
23%.
A 6%.
Oh, okay.
We had a 18% increase in the risk.
Got it.
18% of 5%.
That's right. Oh, well then I'm going to eat my hot dog anyway. No, that's a really high number, and to increase it by a single percent, anything that's that high, that's really scary, you guys. Okay, so those are frightening. By the way, this is just looking at some of that broken out in the amines and what's happening in your gastrointestinal tract as they do that. Is this really in your food? Yes, this is in your food. This is in the very thing. Okay? How does it happen? There's mechanisms of action for that, deamination. By the way, here's the red meat correlate that I have seen, the best research I've seen on it It lies ironically in the very topic we just barely covered. It has to do with this. In carnivores, they don't get any cancer from eating red meats. However, other mammals are known to have a glyconeuramic acid that humans don't. Well, you know about neuramic acid. This is a specific neuramic acid that we don't have. Oh, we've got linkages here in humans where we have a methyl here at this R position where they've got a methanol.
Yeah.
This causes inflammation. Your immune system responds to it, and it leads to increased inflammation, which we believe is highly correlated to the risk of red meat causing cancer. But then you don't get that with fish or chicken. You're like, oh, quite interesting. So that's what we believe is going on. Okay, depurination, what are we talking about? Again, wow, a lot of those happening every day. 10,000 per day, purines lost. Ooh. We're talking about a reaction where this actually pops off and floats away. Well, how would I fix that if I had that problem? If this is floated away, how would I fix this? What do I have for a repair mechanism that I could fix this?
So you have a
If
reactive.
that's my DNA and I just lost the whole purine, it's gone. How would I fix it? Caleb, what are you thinking?
Just bring out the phosphate and pentose, I guess the nucleoside, pull it out, and then put a new nucleotide in.
How would I know which one to put in?
Because you have some,
Oh, the other side has the matching code. I could just fix it. Beautiful. I'm so glad we get double-stranded so we can fix that problem. How would I fix the deamination when it went to a uracil instead of the thymine? Same way. I've got the other opposing strand. I can make a copy. So when does the cancer happen? When I'm in the middle of replication, I open that up and now I don't have one, so I substitute something in or just miss it. Well, is that happening a lot in your cells?
yeah.
All the time. But it would still have to be the right position at the right time. Now you guys, that's beautiful. There's what we're talking about. There's alkylating agents that cause that. Beautiful, beautiful. UV light, I know, we're at time. Okay, so let's see, where are we at? We got to get to Sanger sequencing. We'll come and talk about that when we get back, you guys. As I leave, here's what I'll leave you with. The other cancer-causing element's this, as we walk out the door. If I expose you to high-energy radiation, gamma rays, or just a sunburn, UV light, what does it have the ability to do? It actually interacts and does base pair stacking, okay? It actually causes these to actually covalently link to each other in a way that causes kinks in your DNA and messes you up. Go ahead, go get those sunburns. We've all got them.